Okay. So we are here. 3.3 is on trig derivatives. So we'll do that today and tomorrow. And quiz tomorrow will be on derivatives with the shortcuts. So usual, I'll put you into your breakout groups of 3 or 4, and you can work on them. But they're not due until the following Monday at class time, so you can work on it the whole weekend. Discuss it among your group members in your breakout groups and go from there. Okay, so you really don't have to study for the quiz tomorrow. I mean, you can if you want to, but you don't have to, because you can talk about it and you can use your book, and you got the whole weekend anyway, right? Okay, so we are here. I'll get started with some of 3.3 homework. Okay. I'm going to quickly show you some of the derivations. But again, I'm not going to show you everything as if we were meeting on campus face-to-face and I do them all. So some things you want to keep in mind. Okay, this is a fairly important limit. Okay, so on page 191, and this was question 9 on the last exam. Limit as theta approaches 0 of sine theta over theta equals 1. So you can put it on your cheat sheet if you wish. There are some homework problems that involve that. Again, if you ever forget that, you could just plug in a number like 0.001 or negative 0.001. You'll see 0.9999, something like that. Okay, don't worry about this derivation here. And then the 6 trig derivatives. Again, I'm not making you memorize it because you can put it on your cheat sheet. Your Calc 2 teacher might make you memorize it. So here they are. So derivative of sine is the cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. And then I usually like to go in this order. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. Okay? Notice the co-functions, cosine, cotangent, cosecant, all have a negative. So there's 3 trig functions that don't say co, sine, tangent, secant, do not have a negative. That's in case you had to memorize it. Okay, so I'm not sure if I showed these to you yet. So for those of you that don't have the book and don't plan on getting it, okay, page 196, here are 3.3 exercises. Okay, a little bit more. And then on the next page, some problems there. There we go. Okay. All right, so very rapidly as to the derivation of some of these things. Okay, so frankly, you don't even have to pay attention too much for the next 2 or 3 minutes, okay, but in case you want to know where these rules come from. All right, so we did this numerically. That was question 9 on the test, this limit. Okay, this is a limit that's part of the proof also. To prove this, you could multiply by 1 plus cosine x over 1 plus cosine x, and it breaks down into something like this. And you'd have limit as x approaches 0 of sine x over x, which we know is 1. And this limit, if you directly plug in, you get 0. Okay, so this limit comes out to be 0. Okay, so to prove the derivative of sine, you would use a limit definition, right? The definition of derivative, limit h approaches 0 of f of x plus h minus f of x all over h. Okay, so the derivative of sine of x would be limit as h approaches 0, sine of x plus h minus sine of x all over h. There was an identity like this in trig, right? There was a sign of a sum. Looks like this: sine x cosine h plus cosine x sine of h minus sine x over h. You can gather like terms the right way. So if you gather this correctly, it looks like this. Bring the sine x in front, bring the cosine in front because they are constants as far as h is concerned. You would have sine x times this limit plus cosine x times this limit. Okay. This limit comes out to be 0. We showed that over here somewhere. This limit is 1. So the derivative is sine x times 0, which is nothing, plus cosine x times 1, which is cosine x. So that's a mini proof that the derivative of sine is the cosine. Okay, something similar happens for the cosine x. Okay, you might say you're going kind of fast. Yeah, I'm just blowing through this. You're not responsible for this. I'm responsible for this. So some of you out there might be saying, where did these derivative roots come from? Who made them up? Can they be proved? Yes, I'm quickly showing you, 100 miles an hour, albeit, but these are provable. Okay. So cosine. So limit h approaches 0, cosine x plus h minus cosine x over h for the derivative of cosine. And there's a formula for the cosine of a sum. It goes cos x, cos h minus sine x, sine h. You learned that in trig, minus cosine x over h. You gather like terms, put these two together and factor. Then it looks like this. Factor out the cosine, factor out the sine. So you have cosine x times this limit minus sine x, I messed up there, times this limit. Okay, and once again, this limit here came out to be 0. This limit comes out to be 1. So it's cosine x times 0 minus sine x times 1, negative sine x. So therefore, the derivative of the cosine is negative the sine. Okay, and then for all the other trig functions, tangent. Okay, so we now know the derivative of sine is cosine. Derivative of cosine is negative the sine. All the other trig functions you can write in terms of sine and cosine, and then just use the quotient rule. So for instance, tan x is sine x over cosine x, then you can do the quotient rule, right? So bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the square of the denominator. You have two negatives which make a positive. The numerator comes out to be cosine squared plus sine squared, which is very conveniently 1. So you have 1 over cosine squared, which is secant squared. So derivative of tangent is a secant squared. And something very similar happens for the derivative of the cotangent of x. We do all this stuff. Okay, and then let's say the derivative of the secant. Okay, well, secant is 1 over cosine. So I can do the quotient rule on that. So I'm blowing through this, I understand. So denominator times the derivative of the numerator, derivative of 1 is 0, minus numerator 1 times the derivative of the denominator, derivative of the cosine we now know is negative sine x over cosine squared of x. Double negative here makes it positive sine x over cosine squared x. So technically this is correct, but usually we write it a different way. I can write it as 1 over cosine x times sine x over cosine x. This is the same as that. Okay. And 1 over cosine is secant, sine over cosine is tangent, so secant x, tangent x. And something very similar happens for cosecant. This is a run through it. So the derivative of the cosecant is negative cosecant x, cotangent x. All right, so you say, I didn't follow anything you said. You don't have to. Okay, you're not responsible for this. But if you ever wanted to see this, and yeah, I'll show this all in case anybody wants to go back and look at the video and look slowly at how do we actually prove these. Here they are. You're not responsible for it. And there it is. Okay. Now you can pay attention again, so to speak, because now I'm going to go through problems involving these. Right. So everything that's in this page, you're not really responsible for. I'm responsible for. But in case you're saying, where did these derivative roots come from? I blew through it very rapidly. Okay. But now we're actually going to do some problems from the homework. All right. So the trig derivatives, you can put them on your cheat sheet if you wish. I will now get started on a bunch of this stuff, 1 to 27, 31, 33, and so on. Okay, number 1, f of x equals x squared sine of x. All right, so that looks like a product rule. Okay, so first function times the derivative of the second. We now know the derivative of sine x is cosine x. Plus second function, sine x, times the derivative of the first function, 2x. And a little bit of cleanup. Usually you put the polynomial in front of the trig function. So x squared cosine x plus 2x sine x. Okay, number 5 also looks like a product rule. Y equals secant theta, tangent theta. So y prime equals, so this is the first function, this is the second function. So y prime, first function times the derivative of the second, derivative of tangent theta, we now know to be secant squared of theta, plus second function, tangent theta, times the derivative of the first, derivative of secant theta, tangent theta. Okay. And then just some cleanup. This now becomes secant cubed of theta, and this one is secant theta times tangent squared theta. So you can leave it like that. Or if you want to factor out, you could, but no need to. Okay, number 9, quotient rule. Y equals x over 2 minus tangent x. So that looks like the quotient rule. So quotient rule, denominator times the derivative of the numerator. Derivative of x is just 1, which means you didn't even really have to write it. Minus the numerator, x, times the derivative of the denominator. So what's the derivative of 2 minus tangent x? The derivative of 2 is 0, so forget about it. Negative tangent x, the derivative is negative secant squared of x. This falls under the category of a constant multiplier, right? Pretend there's a negative 1. So the derivative is negative 1 times the derivative of the tangent, which is secant squared. And that looks like a double negative, so make it a positive. So in the numerator, I have 2 tangent x plus x secant squared x all over 2 minus tangent x squared. Looks like I forgot to put a minus there. Sorry, so there should be a minus here. Yeah, a minus there. Sorry about that. So that's what we got. Okay, and then 17 asks you to prove a derivative. Prove that the derivative of the cosecant of x is negative cosecant x cotangent x. So you pretty much just run through the quotient rule like I showed you very rapidly in that other paper that I showed you, but I'll go ahead and do that for you right now. Show that the derivative of cosecant of x with respect to x. Sometimes you hear that language. d dx of cosecant x. We will sometimes say the derivative of cosecant of x with respect to x. I don't think you have to write that down. You just hear me say that, or the book might say that from time to time, with respect to x, meaning x is a variable. Of course, you might say, well, it's obvious x is a variable. Yeah, but in some instances, you have more than one variable. We've already seen sometimes they throw in an a or a b or c. Okay, so this names what the variable is. All right, so cosecant is the reciprocal of the sine, so it's d dx of 1 over sine x. Or in other words, you can say, I'm taking the derivative of 1 over sine x with respect to x. Okay, so I'm just doing what I showed you with that other paper, except slower. Quotient rule. So denominator, sine of x, times the derivative of the numerator. What's the derivative of 1? 0. Minus the numerator, 1, times the derivative of the denominator. So the derivative of sine x we now know is cosine x. All over the denominator squared, so sine squared of x. So that's 0. So I have negative cosine x over sine squared x. So this is technically correct, but most books don't have it this way. I don't want you to know it that way either. The whole idea is to make it simpler. It's easier to memorize, if you had to memorize it, the derivative of the cosecant, if I can write it with a cosecant. Okay, so the trick for this is to write it like this. Negative 1 over sine x times cosine x over sine x. So these are the same thing, right? You can tell if you multiply this out, you get negative cosine x on top and a sine squared x on the bottom, right? And then what is 1 over sine x? Cosecant x. And what is cosine over sine? Cotangent. So there it is. The derivative of cosecant x is negative cosecant x, cotangent x. Okay, so that was that one. Okay, now I'll show you some more. Okay, problem 13 is a little bit tricky because take a look at what's involved with 13. Ultimately, you say there's a quotient rule, right? Y equals t sine t over 1 plus t. But look at the numerator. T sine t, that's a product. So ultimately, right, you have a quotient rule. You have something over something. So you know you're going to do denominator times the derivative of the numerator. But in the process of differentiating the numerator, there's a product rule. So there's a product rule inside a quotient rule, right? All right, so here we go. dy dt, right? Notice this Leibniz notation again. Leibniz. I put that before. Leibniz notation. It's the d notation. It very clearly specifies what the two variables are. It's y and t. And if you just say y prime, you don't know, is the other variable t or is the other variable x or whatnot. Okay, so denominator, 1 plus t. And then by rule, it's times the derivative of the numerator. But to take the derivative of the numerator involves a product. Okay, so product rule. First, t times the derivative of the second. So what's the derivative of sine t? We now know it's cosine t. Plus second function, sine of t, times the derivative of the first. But what's the derivative of t? 1, which means you don't even have to write it. Okay, so I have this. So this is now bottom times the derivative of the top minus the other way around. Top, t sine of t, times the derivative of the denominator. But what's the derivative of 1 plus t? It's just 1, which means you don't have to write it. All over 1 plus t squared. And yeah, you could just leave it. I mean, if you want to do more algebra, you could. I mean, I'm noticing you actually could cancel the t sine of t. Can you see how that's going to happen? If you were to FOIL this out, this is a binomial, this is a binomial, so to speak. So there's going to be a t sine t, right? So that t sine t will cancel that negative t sine t. Okay. So you can do it, but we don't feel like it. We're focusing on the calculus now. So we're focusing on the calculus. Sometimes we'll just skip, the algebra steps. Okay, then 15 has a product inside a product. You're multiplying 3 things together. Theta, cosine theta, sine theta. So you're multiplying 3 things. Now, in case you're wondering, you might say, well, can we make up a product rule of 3 things? Yes, you could. It's usually not worth it. Okay, I would say just figure out what you want as your first function and what you want as your second function. So I decided the first function is theta cosine theta, and the second function is sine theta. So both of them have a trig function. Now you might say, can I have the first function as theta and the second function as cosine theta, sine theta? The answer is yes. Okay, I mean, this is fairly easy to deal with, the theta, but cosine theta, sine theta, there's 2 trig functions there, right? So I'd rather split it so that each one has a trig function. Okay, so I decided to let the first function be theta cosine theta, and the second function is sine theta. Right, so this is my first, this is my second. All right, so here we go, f prime of theta. The way I define it, you copy down the first function, theta cosine theta, times the derivative of the second. So derivative of sine theta we now know to be cosine theta, plus second function, sine of theta, and then times the derivative of the first. But in order for me to differentiate this first function, this itself is a product. So I have to put parentheses and then do the product rule inside a product rule. So I have a product inside a product. All right, so just for this part, theta cosine theta, first function, theta, times the derivative of the second. So the derivative of cosine theta we now know is negative sine theta, plus second function, cosine theta, times the derivative of the first. But the derivative of theta is just 1, so I don't write anything after that. Okay, there we go. And once again, we could clean it up if we feel like it. Don't really feel like it. That's just some algebra and trig, but we're focusing on the calculus right now, so we'll just stop right there and leave it as it is. Okay. All right, and then equation of the tangent to the curve, that recurring theme. 25. You skip B automatically. And I think I've said this before. Anytime you see a graphing calculator icon, automatically skip it. So even though I don't say skip 25B, you know that's what it means. I'm not requiring you to have a graphing calculator for our class. Find the equation of the tangent line to the curve y equals 2x sine x at the point pi over 2 pi. Same thing. You'll see this over and over and over again. So you know the name of the game. Find a derivative, plug in, then do your y minus y1 equals m times x minus x1. Right? So y equals 2x sine x at pi over 2 comma pi. Okay, I'll just make up something. Again, the idea is that there's some graph. You don't have to write this. I'm just doodling. Pretend this is what the graph looks like. And there's some point. So here's some point. There is a tangent line. We're asking where is that tangent line? What's the equation of the tangent line? Notice it depends on what point you pick, right? Because every point has a different tangent line. Right? If I pick some random points here, they will have different tangents to the curve, right? So you have to specify which point are you at. Are you at this point, or this point, or this point, or this point, or whatever, right? So in this particular case, here's some weird graph. That's the point in question. So we're trying to find the equation of the tangent line at that point. All right, so here we go, product rule. First function, 2x, second function, sine x. Okay, so first, 2x times the derivative of the second. The derivative of sine x is cosine x. Plus second function, sine x, times the derivative of the first function. What's the derivative of 2x? 2. So that's y prime. Now I plug in pi over 2. Again, you might say, how come I don't plug in pi? Well, this is x comma y. I plug in pi over 2 for x. I plug in pi for y. So I guess the logic is, okay, anywhere I see x, I'm going to plug in pi over 2. Anywhere I see y, I'm going to plug in pi. All right? So I'm all ready to plug in pi is y, but I don't see it anywhere. And none of the ones that we're doing now are going to have a y until, like I said, further down, section 5 or 6. The derivatives will involve x and y. Then you plug in x and y. For now, we just plug in pi over 2 here, here, and here. So 2 times pi over 2 times cosine pi over 2 plus 2 times sine pi over 2. Right, pi over 2 is 90 degrees. The cosine of 90 degrees is 0. So that's all gone. Sine of pi over 2 is 1. Remember from your unit circle? Right, quick reminder, pi over 2, 90 degrees. What is this as an ordered pair on a unit circle? 0, 1. Right? And remember, the cosine of an angle, you're asking for the x-coordinate, 0. The sine of an angle, give me the y-coordinate, 1. So 2 times 1, which is 2. So the slope is 2. Right? So wherever this graph happens to be, let's say it was here, the slope turns out to be 2. Okay, then just throw it in your point slope form. Slope is 2, the point x1, y1, pi over 2, comma pi. So y minus y1, y minus pi, equals m, 2 times x minus pi over 2, stop. You can leave it there, although if you wanted to go further, I think it comes out to be y equals 2x. Because if you distribute here, that's going to be minus pi, and the minus pi's cancel out. Right. So this is extra. But I think it comes out to be y equals 2x. Because you have 2x minus pi, and the minus pi's cancel out. But you can just stop there, as we said. Okay. All right, next one I want to show you was 33. We'll get this theme quite a bit later on. For what values of x does the graph have a horizontal tangent? Horizontal. That means it looks like this. Horizontal line. What's the slope of a horizontal line? 0. Okay. So horizontal tangent means slope equals 0. How do I find the slope? Derivative. Okay. So I take the derivative, set it equal to 0. Okay, so horizontal tangent means y prime is equal to 0. Okay, so f of x equals x plus 2 sine x. F prime of x, derivative of x is 1. Derivative of 2 sine x, 2 cosine x. Okay, set it equal to 0. All right, so a little bit of algebra. Cosine of x is equal to -1/2. All right, so I draw myself a unit circle. I want the x coordinate to be -1/2. There's an angle there. There's an angle there. That looks like 120 degrees, or 2 pi over 3. This is 240 degrees, or 4 pi over 3. Okay. But you can keep going around the circle or backwards, multiples of 2 pi. Right? So the best final answer is this. X equals 2 pi over 3 plus 2k pi, or x equals 4 pi over 3 plus 2k pi, where k is an integer. All right. Okay, that's what we have for that. Okay, now some of the problems at the end are a little bit different. These questions, 39 to 49, or how far are we supposed to go again? Oops, where are we? 39 to 45. These all involve this guy. Limit as theta approaches 0 of sine theta over theta. Okay, the key thing to notice here, before I get started with this, is this matches this, matches this. Okay? So somehow in these equations, I got to get this and this to match. Okay? Now normally, you're not going to touch this. Okay? This might have a 2 theta, 5 theta. You're not going to fool around with that. But it is pretty easy to fool around with this. Okay, so technically, this, and this have to match. Okay. But one thing we have to notice, okay, you might have this be, let's say, a 5 theta. If theta approaches 0, 5 times theta also approaches 0. 3 times theta also approaches 0. Okay, and right now I'm just talking in the air, perhaps, but I'll show you what I mean once I get started with some of these problems. Okay. So I'll show you for the first one, 39. Yeah, I'll show you 39. Okay, and then after this, I was pretty much done afterwards, and then I'll let you ask questions if you have any, but if you don't, I'm basically finished. Okay, limit x approaches 0 of sine 5x over 3x. Okay, so how do you do that? Yeah, there's too much stuff here that you've seen. I can possibly hide this. Okay, here's the original. So the game you have to play is this. This is 5x. I need this also to be 5x in order to get the limit. In other words, I have to force the denominator to have a 5x. And you might say, can I change this? Not easily. Not when there's a sign there. If this were 3x over 3x, that fits the bill. Okay, the problem is it's not easy to change sine of 5x to sine of 3x. it is fairly easy to fiddle with this. So I want the denominator here to be 5x. How do I do that? Simple. Multiply top and bottom by 5/3. So why 5/3? I need to change the 3 to a 5. So I divide out the 3 and multiply by 5. Okay? So do you agree if I multiply these out now, I get a 5x in the bottom because the 3's cancel out? This 5/3 I'm not really going to use. I'll just factor it outside. So this comes out in front. 5/3. Limit x approaches 0, sine 5x over 5x. This is the way you want it. Usually you want this to match this. Now you say, what about this? Okay. It's actually going to work. Okay. So let me show you again. This is kind of a complicated concept, perhaps. Okay. Yeah, if you want to write this on your cheat sheet, you may. Limit theta approaches 0, sine theta over theta. Yes, theoretically, that, and that all have to match the same angle. But the main thing is that these two match. If this approaches 0, you can kind of get away without it. So again, that, and that have to match. But so 5x, 5x. So you might say, in order for this thing to work, that should be a 5x, which is true. But here's the idea. If x approaches 0, so does 5x. If x approaches 0, 5x approaches 0. So if x approaches 0, then 5x approaches 0. Okay. Suppose I plug in x is 0.00001. This would be 0.0005, which is still approaching 0, right? I can get even closer. 0.00001. This would be 0.00005. It's still very tiny. All right, so in other words, the whole idea is that, yes, I can now replace this whole thing with 1. Okay, so I have 5/3 times 1, which is 5/3. Okay. So that's that. All right, and that's as much as I was going to do today. Okay, so I'll make this disappear. In case you're wondering what's going to happen tomorrow, tomorrow I'll do a few more of these. Okay. I might sneak in a little bit of the next section, but then after that we'll stop and take our quiz. The quiz will just be derivatives of everything we have now. So I might have some trig, I might have product rule, quotient rule, ease, sum and difference, and all that kind of stuff. But again, I would say don't even study with it. You can help each other out. You've got your other team members, your breakup group members that help you on the quiz. And it's not due until class on Monday at 12:10, so you can even have the whole weekend to work on it. Okay? All right, so let me stop to share. Check the chat. And let's see, Prasanna, you help me out, I'm sure. Right, so theta is just like x, it's a number. Okay, so you have to use the product. There was a product inside a product. Okay, so 2k pi versus k pi. Yeah, in general, you're going to have 2k pi. You would only use k pi if the two solutions happen to be 180 degrees apart. Okay, if they're 180 degrees apart, then you can use k pi. All right. So that's that. Okay, re-explain 33. Okay, which is almost like everything we had here, I guess. So go back to that, I guess. If I can find how to do that. So this is dependent on your knowing some trig. Okay, so I take the derivative, set it equal to 0 because it says horizontal tangent. Solve for cosine x, you get -1/2. So I'm saying the cosine of what angles comes out to be -1/2. That means on my unit circle, I go halfway toward -1, right here. Then it says cosine theta. Okay. That means you want the x coordinate to be -1/2. There's one angle here, there's an angle here. That looks like 120 degrees, which is 2 pi over 3. That looks like 240 degrees, 4 pi over 3. All right, so I know I have 2 pi over 3 and 4 pi over 3. But I can keep adding 360 degrees or 2 pi radians. or subtract. Okay, so I add a multiple of 2 pi, 2k pi for 2 pi over 3 and 4 pi over 3 also. Okay, but if you had a situation where the angles were 180 degrees apart, so let's say you had one at pi over 4 and 5 pi over 4. So theoretically, you could still say pi over 4 plus 2k pi, or 5 pi over 4 plus 2k pi. But since these are 180 degrees apart, you can just add pi radians, another pi, another pi, another pi. So then you would just say pi over 4 plus k pi, where k is an integer. Okay, so that's sort of a review of stuff that you had in trig right there. Okay. Do you have to draw the unit circle? I mean, you don't have to. You can just know it. I like to draw the unit circle because it helps me remember stuff and helps me for teaching. But technically, no, you don't have to. How do you know to set it equal to 0? It said horizontal tangent. Horizontal tangent means derivative equals 0. Okay. And let's see. 3.2, number 11. Okay, so let's try that. This book is heavy, unfortunately. Okay. 3.211. And somebody asked for 31B and C. I guess you're talking about which section? Probably 3.3. Okay. So 3.3, 31B and C. Okay. I see that in the chat, but I may not be able to see the chat anymore once I switch over. Okay. 3.211, f of y. One over y squared minus 3 over y to the 4th, y plus 5y cubed. You basically FOIL it out. First, outer, inner, last. So that times that is 1 over y. That times that is 5y. That times that is negative 3 over y cubed. That times that is negative 15 over y. Okay. And these two combine to be negative 14 over y. All right, so it's pretty much just going to be power root. So negative 14y to negative 1 plus 5y minus 3y to the negative third. Okay, so remember, in order for you to use the power root, you can't have the variables in the denominator. We don't know how to differentiate 1 over f of x or f of y. It's just f of y. Okay, so this would be 14y to negative 2 plus 5 plus 9y to the negative 4. And negative, whoops, positive 14 over y squared plus 5 plus 9 over y to the 4th. Okay. All right, then 31B and C of section 3, I believe. here. F of x, tan x minus 1 over secant x. Simplify by writing in terms of sine and cosine. Okay. So tangent is sine x over cosine x minus 1. Secant is the reciprocal of the cosine, so I'll multiply by cosine. So that gives you what? Sine x minus cosine x. So prime of x is cosine x plus sine x. And then part C requires you to show that they're equivalent. Well, you have to know the derivative of f prime. So this is part B. Part C, I guess I have to differentiate. So using the derivative from this is denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. Okay, so somehow that's going to be the same as this. Let's see. Secant cubed x minus, okay, we've got to be careful here. Secant x tangent x times tangent x, right? So secant x tangent squared x minus a minus, so plus secant x tangent x all over secant squared x. Okay, so what can we do here now? Let me just actually divide through. So this is going to be secant x minus tangent squared x over secant x plus tangent x over secant x, I think, unless I made a mistake. Okay, so this is 1 over cosine. Tangent squared is sine squared x over cosine squared x. Reciprocal of secant is cosine, so there's a cosine on top. And tangent is sine x over cosine x, and times the cosine x. Cancel, cancel. Cancel, cancel. So I have 1 minus sine squared x over cosine x plus sine x. 1 minus sine squared is cosine squared. Cosine squared x over cosine x plus sine x. This pretty much just turns out to be like those trig identities, right? Remember those trig identities you did? You should try to get this to match that. So we finally got it, cosine x plus sine x. So this is indeed equivalent to what we got over here. Okay. So that's that. All right, folks, I think that's pretty much about it. And let's see. Yeah, I think we're good there now. So, all right, that'll do it for today, folks. So tomorrow I'll lecture for a while, and then we'll have our quiz, but the quiz, again, isn't due until the following Monday. You can work it out on the weekend, as usual. All right, so I'll do it, everybody. So have a good afternoon. We'll see you later.
Thank you, Professor.
Thank you.